We saw bootstrapping as an example of an exact method. In this part, we will now formalize the exact method and see how it can be written as a linear equation. We will highlight some issues and propose some solutions to these issues. One solution, as we will see, is the bootstrapping method. I will also show you another alternative solution to it, which builds on the pseudo-inverse of the cash flow matrix. Formally speaking, the market data that is given to us at the spot date T0 is stacked into a vector P of n market prices. Each of these instruments yields a cash flow Cij, so that the value of instrument I is given as the sum of the discounted cash flows Cij. Now the special thing about this sum is that we will sum over all possible cash flow dates, and there are capital N of them, even though instrument I may not have a cash flow at that date. We will then simply put Cij equal to 0. So market gives us the PIs and it gives us theCijs, the cash flows on the dates Tj. What is not known is the discount curve. We stuck the discount curve into the vector D and we rewrite this equation here as this matrix equation. The next step is now to bring the data into this form. While this is pretty straightforward if the market data are prices of coupon-bearing bonds, this is less so in case where market data is LIBOR, forward rates, and swap rates. Let's start with coupon bond market data. As an example, we look at these quotes of UK government bonds on the 4th of September of 1996. We have 9 bonds. They come with coupons ranging from 7% to 12.25% on a principal of 100. We see in the middle columns the next coupon dates, and we see in this column here the maturity dates of the corresponding bonds. We also see their dirty prices. So if we start to count and order the cash flow dates, we see that it's bond number 3 that pays the next coupon. The next bond is bond number 9, and the third cash flow comes from bond number 5. We also see from that table that bond number 1 is the soonest to mature bond. The next coupon date coincides with its maturity date. So there is only one cash flow left for this bond. UK government bonds have semi-annual cash flows. So bond number 2 has 3 cash flows left, and so on and so forth. If we summarize, these UK government bonds data on the 4th of September of 96 are prices of coupon-bearing bonds that pay semi-annual coupons. The day count convention is actual by 365. The number of market prices given is 9, and the number of cash flow dates, if we sum them up, bond number 1 had 1 cash flow left, bond number 2 had 3 cash flows left, and so on and so forth. Summing up gives us 104 cash flow dates. The first one is the one from bond 3, the second one is the one from bond number 9, and the third one is the one from bond number 5, as seen on the previous slide. We can summarize these cash flows into the matrix C. In the first row, we see the cash flow of bond number 1, which matures and pays the principal plus the 10% coupon rate. Remember that coupons are paid semi-annually, rates are annualized, so the interest paid on the maturity date is 5. Similarly, the second bond will pay a coupon of 4.875. The third bond, which is the bond with the earliest next coupon payment, pays 6.125, and so on and so forth. Recall that in total we have 104 cash flow dates. So what we see on this slide are the first 10 columns of a 9 times 104 cash flow matrix. We also see that it is sparse. Most of the entries are zeros. Now let us bring into the price cash flow form the LIBOR and forward rates. The LIBOR rate prevailing at T0 with maturity date capital T can be casted in the form by giving it a price P of 1 at T0 and giving it a cash flow of 1 plus delta times the rate at maturity capital T. A forward rate, remember, was derived from a forward rate agreement which corresponds to a cash flow of -1 at time T1 and a cash flow of 1 plus delta times the forward rate at T2. The present value of these cash flows at time T0 is 0. These carries overs to swap contracts as follows. Let the fixed rate be K and let T0 up to Tn denote the reset and settlement dates, where for the sake of notation here we assume that the delta here is constant. If K is the swap rate, then this relation here holds. So if the swap is spot starting, if capital T0 equals the small t0, this is just value 1. We take it to the left-hand side and we see that we got a price cash flow scheme of price 1, cash flows delta times K and 1 plus delta K at the maturity. If the swap is forward starting, we take this equation literally as is. The price is 0 of a cash flow of -1 at time T0 plus cash flows of delta K at times Tj and 1 plus delta K at times Tn. Summarizing these formalizations, at the spot date T0, LIBOR and spot starting swaps have a notional price of 1. Forward rate agreements and forward starting swaps have a notional price of 0. Let us now come back to the example with the US money and swap market data from the 1st of October 2012. That is the example that we saw in the bootstrapping example. Remember, the day count convention is actual by 360. We are given 3 LIBOR rates, we are given 5 futures quotes, and we are given 9 swap rates. We thus have 17 market prices. The corresponding cash flows are 3 for the LIBOR, 6 for the futures, and 30 for the swaps, adding up to 39. The ordered cash flow dates are T1 is the 2nd of October, which is the overnight LIBOR maturity. T2 is the 5th of November, which is the 1-month LIBOR. T3 is the 19th of December, which is the first reset date of the first futures contract here, and so on and so forth. If we stack these cash flows into the 17 times 39 cash flow matrix C, it will look like this. In the first row, we have the cash flow of the overnight LIBOR. Second row, we see the cash flow of the 1-month LIBOR. In the third row, we have the cash flow of the 3-month LIBOR. In the fourth row here, we see the cash flow -1, which is from the first futures contract, and the cash flow, the corresponding cash flow at the maturity. Similarly for the remaining futures contracts in this middle part of the matrix. And then in this first row corresponding to the swap contracts, we have the 2-year swap, which pays 2 annual coupons as shown here. The next swap has a length of 3 years and it pays 3 coupons, and so on and so forth. Again, what we see here is not the full matrix, we just see the first 12 columns, in fact, of 39 in total. Again, we see the matrix is full of zeros and is sparse. On the other hand, it is also obvious that this matrix has full rank. The 17 rows are linearly independent. The linear system for the discount curve, hence, has at least a solution. It has in fact infinitely many. Summarizing, these exact methods typically lead to linear systems for the discount curve D, which are underdetermined because the number of equations, small n, is much smaller than the number of unknowns, capital N, in general. As a consequence, there exist many discount curve solutions. Which one is to choose? Now let's recall the bootstrapping example from the previous section. A moment's reflection shows that we in fact synthetically created new market instruments by the linear interpolation of swap rates and LIBOR rates. We actually created just as many new market instruments as there were equations missing, capital N minus small n. The extended market data then gave us a capital N by capital N cash flow matrix that was invertible. And so we could solve for the unique discount curve in that case. Bootstrapping is one possibility to deal with the issue of an underdetermined linear system. As an alternative solution, we will now see what the pseudo-inverse of the cash flow matrix can tell us. Here is the idea. Instead of estimating the discount function D directly, we estimate instead a vector of weighted increments of the discount curve, as shown here. The first entry is the T1 bond price minus 1, which is the T0 bond price, divided by the square root of the time to maturity. The second entry is the difference between the T2 bond and the T1 bond divided by the square root of the difference of their maturities, and so on and so forth to the Tn bond price minus the Tn minus 1 bond price, again weighted. We can write this in matrix form as product of a weighting matrix W times M applied to D minus the first basis vector. The weighting matrix W is the diagonal matrix with these entries on the diagonal, and M is this matrix as shown here. There is in fact a one-to-one relation between this vector of weighted increments delta and the original discount curve D, as shown here, where the inverse of M can be explicitly computed as shown here. We can thus reformulate and restate the linear matching problem as this linear system here, which is now an equation for the vector delta. Remember that market data gives us the cash flow matrix C. M is an auxiliary explicitly given matrix. W is the diagonal matrix consisting of the weights derived from the maturity dates. P is the vector of market prices. Again, these are more unknowns than there are equations. But typically, the small n times capital N matrix A has full rank because C has full rank. So we can form the pseudo-inverse, which gives us a particular solution to the linear system that we saw on the previous slide. By the definition of the pseudo-inverse, this is in fact the unique solution of the linear system with minimal Euclidean norm. If we write down what this Euclidean norm looks like, we now understand in hindsight why we have weighted these bond price increments by the square root of the difference of the maturity dates. Indeed, the square here implies that we can omit the square root and multiply instead these expressions with delta. So this gives us a first order proxy of the integral of the derivative of the discount curve squared with respect to maturity. We thus obtain the smoothest possible discount curve according to this criterion. Let us revisit the example that we saw in the bootstrapping example, US market data from the 1st of October 2012. We had 39 cash flow dates, including the spot date. We had 40 points on the discount curve. Discount curve is shown here on the left-hand side and zoomed in on the right-hand side as function of time to maturity. The implied yield curve and the forward curve is still irregular, but the comparison shows it is smoother than the one that we got from the bootstrapping. Summarizing, the pseudo-inverse provides a valuable alternative to the bootstrapping method. It is an exact method that is very simple to implement and that yields the smoothest possible yield curves.